think the last time I visited the Institute, I was a prospective graduate student, and I remember sitting at lunch with Nick Katz and Andrew Wiles, probably while they were in the midst of proving Fermat or working it out, and having Nick Katz convince me not to come to Princeton. No, it was just basically he made the argument that I really didn't know what I was talking about, and so I decided that maybe I had some idea that I wanted to do hyperbolic geometry, and he didn't think I knew that. So in any case, it was an interesting lunch. So what I'd like to do today is, well, continue with a theme, really. I don't know that this is going to work. Let's start over here. So really, I'd like to continue to explore, well, let me say first, this is joint with Ken Bromberg, and it's a sort of ongoing project to understand things about volumes of hyperbolic three-manifolds in Weil-Petersson geometry on Teichmuller space and moduli space. Okay, it turns out on the moduli space of a surface S, so there's some fairly well-developed connections here, but they somehow continue to get richer and more interesting as time passes and people work on different aspects of the question, in particular the connection to hyperbolic three-dimensional volume. Okay, in particular those that have some relationship to the surface S. So key cases here are three manifolds that fiber over the circle with fiber S, or quasi-Fuchsian three manifolds. And there's an intimate relationship here too. So I started working on this a while back, and it's dovetailed with work with many other people. But in particular, there is some connection in both of these cases, but it was somewhat unsatisfying even as I was working it out, in that it involved a kind of combinatorial interface. Called Pant's distance. Okay, and this is a combinatorial notion related to isotopy classes of decompositions of the surface S into pairs of Pants, having to do with a kind of elementary move distance. And the idea is that if you can show that there's a coarse relationship here, sort of in the sense of quasi-isometry, and likewise some sort of coarse relationship here, then you get this one. And that was the strategy. So this involves certain kinds of combinatorial constructions, and a lot of work of, again, a lot of people. And I should say that though on the level of volume, one only needs this sort of level of understanding of these combinatorics, this was the key to understanding in general the model manifold, a bi-Lipschitz model for elements in the space of quasi-Fuchsian, so quasi-Fuchsian hyperbolic three manifolds in work of Minsky and our joint work with Canary and Minsky. So even though this seems sort of more facile to connect it in this way, it's always somehow seemed worth investigating whether there's a more natural connection or whether one can see Weil-Petersson geometry and volumes as related through more direct or analytic constructions. So this, I think, is kind of promising. Recent developments have lent themselves to this. So there's this kind of a new tool. Well, let me make one or two other remarks. So there's lots of obvious connections in terms of just the general structure. Like, for example, the volumes of hyperbolic 3 manifolds are well ordered with order type omega to the omega. And so, we had this kind of beautiful study of what are the bottoms of the accumulation points, what are the sort of least elements, and then the next least element in the sequence, et cetera. And so the study of these volumes actually, in absolute terms, can also be carried out in the setting of 3 manifolds fibering over the circle, where the same order type holds. And there's so in joint work with Minsky, showed that in fact the closed geodesics, Weil-Petersson geodesics on the moduli space have a similar property. One has to be a little careful about the definition. I'll say more about that later. But they also have these accumulations corresponding to iterated Dane twists. So there's sort of a notion of a billiard path on the compactified moduli space. And closed geodesics can be extended to somehow billiard paths that bounce off the completion. And if one allows that as a notion of a closed geodesic on moduli space, then the same order type holds. But it's also clear that there's no, at this point, explicit formula to relate the two. So in joint work with Juan Soto, there's no function, no continuous function for which f of volume of whatever equals the Weil-Petersson translation length. And we'll see that's the relevant quantity. Okay, but there still appear to be some really interesting some analytic bounds that one can obtain. In other words, one can kind of get around, at least in one direction so far, factoring through this combinatorial machinery. And that comes out of the notion of what's called the renormalized volume. So I'll say a couple of words about that. And this is, well, I guess this was introduced by Witt, and I can't claim to really know the details of how it was introduced, but it's been used more recently by Jean-Marc Schlenker and in work with his collaborator, Kirill Krasnov. So what they do is they sort of replace the idea that the convex core volume is an interesting thing to look at for an infinite volume 3 manifold with a way to kind of rescale the volume as it, normally you have an end of a hyperbolic 3 manifold that's geometrically finite. The volume's exponentially growing in the distance from the boundary of the core. They have some correction term which gives you a finite quantity. And this notion of renormalized volume has some very nice variational properties which relate to Teichmuller space. And I guess the other tool that I think is interesting here that comes up is the notion of inflexibility of hyperbolic 3 manifolds. And this is sort of some of my work with Ken Bromberg. Which is a generalization of the rigidity theory due to Mostow and Sullivan. So in this rigidity theory for a closed or finite volume hyperbolic 3 manifold, any Weil-Lipschitz deformation of the hyperbolic structure is homotopic back to an isometry. Likewise, in Sullivan's case, if you have domain of discontinuity or conformal boundary for your hyperbolic 3 manifold, as long as you preserve that conformal structure, a Weil-Lipschitz deformation is homotopic back to an isometry. What inflexibility gives you is a kind of more analytic characterization of what the best, even if you have some deformation at infinity, how that deformation decays in the distance into the convex core. So that comes up at least in our proof of what I'm going to talk about today. So those are just some preliminaries. Let me give you just the main context will really be these three manifolds that fiber over the circle, okay? So what we have, some surface diffeomorphism. S is, well, it'll be a closed surface for now of negative Euler characteristic, okay? And one can form the mapping torus M psi just by gluing one into the other. Or maybe that's M sub psi inverse, depending on your conventions. And Thurston showed that this is, of course, hyperbolic if and only if psi is pseudo-Anosov. And basically, pseudo-Anosov just means there are no obstructions to this manifold being hyperbolic. So psi doesn't permute. Psi acts freely, if you like, on the set of all simple closed curves on the surface. So if it were to bring a simple closed curve back to itself under some number of iterates, there would be an essential torus in the manifold. Of course, this is also, this element psi represents, if we take its isotopy class, it lives in the Teichmuller modular group, so it's an automorphism of the Teichmuller space, hyperbolic structures on S. And pseudo-Anosov here means that it acts like a hyperbolic automorphism. So in all the metrics on Teichmuller space one is interested in, it preserves an axis, a geodesic axis, and translates along it by some amount. Okay? And that translation length, or that amount it translates, we call the translation length. Okay, now as an automorphism of Teichmuller space, this behaves like a covering transformation, if you like, over the moduli space. So the axis descends to a loop on the moduli space in the quotient, and the length of that loop is this translation length. Again, I haven't specified the metric, but it'll become clear enough what I mean here. Okay, okay, so indeed, so let's just say when this manifold is hyperbolic, it has well-defined hyperbolic volume. Okay, and this volume is an isotopy invariant of this monodromy map psi. So it's some number associated to this element of the modular group, and we're sort of interested in what it corresponds to over here. That's the Teichmuller, the Weil-Petersson translation length. Okay, so in the level of moduli space, so psi determines an invariant axis in, well, the Teichmuller metric is the usual one, but we're going to consider the Weil-Petersson metric, just coming from a different norm on the L2 norm on the space of quadratic differentials. Okay, and this translation length is another such isotopy invariant. Okay, so the fact that there's this axis here is due to Daskalopoulos. Wentworth. One needs to make sure that the normal sort of minimization process doesn't hit the completion, because the Weil-Petersson metric is not complete on the moduli space. Its completion, in fact, is the Mumford-Deligne compactification. Deligne-Mumford compactification, excuse me. So what is this Weil-Petersson metric? Well, it comes from the cotangent space, or the co-norm, L2 norm, on the quadratic differentials. On a quadratic differential psi, one integrates 5 phi bar divided by rho over the surface x. And this gives you the Weil-Petersson norm squared, L2 norm squared. Okay. So I guess what this diagram, the main result of it, was to show that, in fact, that if we take the translation length we'll call, so psi is my automorphism, my pseudo-Nosov automorphism of Teichmuller space, and I take the Weil-Petersson translation length, that this is comparable with a constant, multiplicative constant depending only on the genus of the surface to the volume of the hyperbolic mapping torus. So the volume psi is, well, I'm going to write a squiggle. I could write a squiggle here, or I could sort of say it lives in the interval 1 over k times the translation length. Okay, so where k depends only on s. Okay, and this was a corollary kind of by, well, understanding the structure of when a three-manifold fibers over the circle, you can think of it as a limit of its cyclic cover is a limit of quasi-Fuchsian manifolds. And this result came out of really a theorem about the convex core volumes in the quasi-Fuchsian case. So let me just make one other remark here. So what is this combinatorics? Well, it comes out of, again, this notion of Pant's distance, which really just comes from the notion of a combinatorial move on Pant's decompositions. If I have a Pant's decomposition of a one-hole torus, which is just a single simple closed curve, I'm allowed to switch that to another Pant's decomposition coming from a curve that intersects it once. Another local picture comes from a four-holed sphere sitting on the surface. And in that case, I'm allowed to change my Pant's decomposition, which contains this green curve, to a curve that intersects it minimally, but in this case twice. But I could choose any of these. Okay, so that gives me a z's worth of possible ways to change one Pant's decomposition into another. And this is reminiscent of, in fact, it is exactly the structure of what's called the fairy graph, one can draw without lifting one's chalk, etc. Okay, which connects edges, which connects vertices, rational points where the determinant PQRS is equal to 1. Those correspond to slopes, or in a homology basis for the punctured torus, of a basis. So we have, if two points are joined by an edge here, they form a standard basis. Okay, so we want PQRS equal to 1. Okay, so when I say the Pant's distance, what I'm really saying is, for the one-hole torus, I look at how many edges it takes me to get in the fairy graph. I'm not sure I've chosen a geodesic here, but probably from one edge to the next. I mean, from one vertex to the next, so between rational points. Okay, but this has an analog in higher genus, which is just this Pant's complex. Okay. Now, I guess what I want to emphasize here is that, as I noted, there's a z's worth of possible moves one can make from one curve that corresponds to a Dane twist action about the curve that's fixed. So what this should suggest is that Dane twists do not increase pants distance. And likewise, 1n Dane fillings do not increase volume. In fact, they increase it in a bounded way. Okay, so if one performs 1n Dane filling here, the sequence as n tends to infinity converges to a finite volume, now cusp hyperbolic 3 manifold. So that's the motivation for the considerations. But let me move to the more general setting. Because indeed there's always a great deal of terminology to unpack here, but the genesis of the theorem is a more general theorem for the quasi-Fuchsian case where one has well, let me make the following remark first. So the referee for this paper noted that, well, there's an analogous theorem in the quasi-Fuchsian case. If one had more explicit comparison between the convex core volume of quasi-Fuchsian manifolds under pseudo-Anosov iteration and the volume of the limit, then this would be more immediate. So in particular, how does one obtain this hyperbolic structure? How did Thurston, I should say, obtain this hyperbolic structure? If you consider the pseudo-Anosov mapping class, he took the double iteration on the quasi-Fuchsian set of quasi-Fuchsian hyperbolic 3 manifolds, just starting at the Fuchsian one if you like, on Teichmuller space. Okay, so these are the bare simultaneous uniformizations of a pair of Riemann surfaces. We caricature them like so. So there's a hyperbolic 3 manifold with cross-section as surface S and a conformal structure at infinity, phi to the minus n x here, phi to the n psi to the n x here. And, well, as it happens, the convex core gets thicker and thicker, although it wasn't really known precisely how quickly. And there's a natural way to see a translation in the homotopy class of psi here that is of a bounded bi-Lipschitz type. So it becomes more and more periodic as n tends to infinity. And in fact, the limit is a periodic hyperbolic 3 manifold, Q infinity. So we'll call these Qn. And these tend, at least in the deformation space to start with, that's all you need at first, to Q infinity, the cyclic cover of the 3 manifold that fibers over the circle. So this is a periodic manifold that admits an isometry in the homotopy class of psi. Okay, but I just want to say that so there's an analogous theorem for the volume of this convex core. So this is the smallest convex submanifold of the quasi-Fuchsian manifold whose inclusion is a homotopy equivalence, that the Weil-Petersson distance is related to the convex core volume. Yes, erase this. In the same way, K1 plus K2. Okay. And what the referee noted was that if one knew, so if the volume of the core of this nth iterate, Qn, sorry, we're close O of 1 from 2n times the volume of 2n fundamental domains, then in fact this theorem would be immediate, which seemed like a nice observation, but I didn't really know immediately how to prove it. Then we, so in the intervening period, we noticed that some of the techniques we were developing around inflexibility that I mentioned might show this, but I guess there was a question of whether it was worth the trouble. So what I guess is the new development? Well, first of all, we got asked whether we had. So this was, I included this as a remark in the paper that the referee had mentioned this, and then various people started asking me whether we had done this. And I should mention that there's parallel work of Kojima and McShane along the lines of what I'm about to say, and I'll try to explain what their role in all this is too. But Jean-Marc Schlenker, using his technique of renormalized volume, noted that, again, for the closed surface case, there exists some constant kg so that the volume of the core of any quasi-Fuchsian 3-manifold, not necessarily this double iteration, admits a very explicit, in other words, he gave a very explicit form for this K1. So we have an explicit bound of the form 3/2 times the square root of the Poincare area. Okay, so this is just 2 pi times the Euler characteristic, absolute value, times the Weil-Petersson distance, plus, again, some additive genus constant. Okay, so, well, if one has something that nice, then this observation becomes more interesting because one can divide in this setting where we replace this with Qn and this with, so if we replace this with Qn and this Weil-Petersson distance with the double iteration, well, we'll just put x again. Then dividing both sides by 2n gives something like the volume theorem up here for the fibered case. Okay? So in other words, this is going to start, if you divide this by 2n, this starts to look like the translation distance of psi on the Weil-Petersson metric. And this starts to look like, well, the volume of this core divided by 2n, which, if it were in a bounded relationship with 2n times the volume of the I wanted to say not mn here, I'm sorry, m psi, the volume of the fibered 3-manifold, then you get this relationship with an explicit constant that looks like this. Okay, so that's, so that basically we were asked about whether this was true, and in the meantime, there was a preprint of Kojima and McShane that gave a similar argument in the Teichmuller case without a proof of this result. We were interested in these Weil-Petersson applications, so we worked this out independently. And basically, at the same time we worked it out, they gave an independent proof as well. And there's another. Yeah, so they did the Teichmuller case. Well, the problem with the Teichmuller case is that you get an. The statement is that. It's just not as good. It's a, well, you have to take away the square root. Okay, because, yeah, it's Cauchy-Schwarz, which I've discovered of all the things, successful applications of Cauchy-Schwarz may be my most difficult challenge in mathematics. But, but in any case, the Teichmuller distance, in these Dane twist iterations I was mentioning up here, Teichmuller translation distance clearly grows. It grows like log of the chain twist, whereas the volume of the 3 manifold stays bounded. So it's not as tight a bound as the Weil-Petersson bound. But if one there are certain kinds of optimization problems for which that's not really in play, and those are very good questions if you're interested, for example, as what we're going to talk about in a little bit, in things like the Teichmuller systole for moduli space and other things of this nature. So what Ken and I showed star over there. Let's call this star. Was indeed that the volume of the mapping torus is less than or equal to 3/2 times the square root of the area of S times the Weil-Petersson translation length. And yes, so by Cauchy-Schwarz, you get immediately from this 3/2 area S times the Teichmuller translation distance. Okay. So, and I guess this all works. So I started out with no boundary components. There's a sort of a branch cover trick suggested to us by Ian in the Teichmuller case, which works in the Weil-Petersson case if you fuss around a little bit, that gives this for general SGN. Okay. So,
Jeff, do you know explicit, I mean, your original theorem, there's both an upper and a lower.
Yeah, good question. So it doesn't seem to be as straightforward. I mean, so here somehow the reason this works is you end up using this variational formula for something called the renormalized volume, which I haven't defined yet, to go from the Fuchsian manifold to the quasi-Fuchsian manifold. You have a path in Teichmuller space. The variational formula, as it turns out, gives the length of that path times an explicit constant coming from Nahari's bound on the Beer's embedding. So there's a way to write the derivative of the renormalized volume as just the standard product between a quadratic differential coming from the Schwarzian of the Beer's embedding times the tangent vector to the path in Teichmuller space. So you just integrate that along the path. And that sort of gives that very straight, both of these cases you can work it out in terms of that integral. What's harder to see is how you would choose a path smartly so that you could get the other direction, that the Teichmuller or Weil-Petersson distance was forcing the volume to grow at a definite rate. So that's an interesting question. Various people are thinking about it, I think. Right. So I want to say various things about this, but I guess one of the things I'm particularly interested in here is that out of this and out of this great work on minimal volume hyperbolic 3 manifolds, what the smallest volumes in fact are, out of it comes some first explicit lower bounds for Weil-Petersson systoles and diameters in moduli space. Likewise, in MS. Likewise, one is able, if there's kind of a movement now to try to effectivize, as the term goes. Not sure I approve of the term effectivize, by the way. But in any case, make effective various of these constants. And there's a whole litany of constants in the literature that depend in some way or other on the genus. But it's been difficult to kind of unify them because there's always some geometric limit argument at some point in the process. So you show that there exists some constant. But there seems to be forward progress on eliminating the reliance on the surface in the discussion, which is exciting. Okay. All right. So maybe I'll just stop and ask if there are any other questions about this setup. Which numbers? Okay, right. So, well, I mean, I've been kind of badgering Scott Wolpert for years, for example, about what. So as it happens in the Weil-Petersson metric on the upper half plane, so this is a Teichmuller space on the punctured torus or the four-hole sphere, the imaginary axis, well, it's really just one of these edges of the fairy graph. It has some finite length, and there's some kind of gross upper bound one gets from the original incompleteness argument of Wolpert, non-completeness argument of Wolpert. But lower bounds, who knows? And so what we get is kind of the first actual explicit number. It's not a number that says what the length is, but it's an explicit number that's in terms of some volume that says that it's at least that. So in terms of, well, I mean, this is just in genus 1, but in terms of the diameter of the moduli space, you get something from, well, out of Will Cavendish and Hugo Parlier's argument, where they bound from below in terms of whatever this length is, the diameter of the, and then one nice corollary is an explicit counterexample to Juan's question about whether the normalized Weil-Petersson moduli space has diameter tending to 0. The answer is no, of course. But in any case, whoops, here we go. Okay, so maybe I'll just make two quick remarks. So in terms of, so I said I was going to say something about renormalized volume. Okay, again, what his work suggests is that thinking about the convex core volume may not be the most natural way to try to understand these kinds of questions. And so what they do is they define something. If you have, okay, so this is for any infinite volume hyperbolic 3 manifold M, and if we have a convex submanifold with smooth boundary, then we can consider the quantity, the sort of W volume associated to N, which is the actual volume of the convex submanifold minus a correction term, which is 1/4 the integral over the boundary of N of the mean curvature with respect to the induced area. Okay, so imagine as you take bigger and bigger, you could take, a radial R neighborhood of this, okay, and let R get larger and larger, and the area is growing, but the mean curvature is also tending to 1 as the surface gets more and more convex. So you have this correction term that cancels that extra volume that you get. It's the way, at least the way I think about it. So this doesn't seem very canonical, but if you then, so what they argue is that if you take, say, SR, which is like the boundary of the set of X and M within distance R, okay, this is some surface, that these R's, S sub R's, converge in the conformal class to the conformal class of the boundary. So if you correct again and take, so if I, R, in their terminology, is the induced metric on SR, then you can scale and take the limit of 2e to the minus 2r times this metric, and that converges to some conformal structure. And the idea is that somehow there are different ways to realize this family. I mean, you could start with a different n, but this quantity depends only on this limiting structure. Okay, so Wn depends only on this limit I star. Okay, and if you fix, so it's an actual metric, or you could take the limit in the conformal class by forgetting this and just take, just forgetting the scaling factor. You don't assume that if you start with an arbitrary convex n, but it turns out that this quantity is maximized when it has constant curvature. Okay, so Wn maximized among choices where the area is fixed when I star has constant curvature. Okay, and the way the logic proceeds is that then one chooses area 2 pi times the absolute value of the Euler characteristic, the Poincare area, and the hyperbolic metric. Okay, so the hyperbolic metric maximizes Wn, or W, I guess we can still just write it Wn, when area is chosen to be 2 pi times the Euler characteristic, and then this quantity is called the renormalized volume. Whoops. With I star equals hyperbolic. Okay? So that is a canonical number associated to M.
That's equal to 0, you're saying?
Sorry?
That difference is equal to 0?
Sorry, that was a dash. I don't know if it was an M dash or an N dash or, okay, so equals. Thanks. Okay, so, well, what is this good for? I mean, a couple of the properties that satisfy some kind of monotonicity property with respect to other well-known choices of metrics, which allows you to show things like that the volume of the core is within O of 1. And well, let's pass to quasi-Fuchsian manifolds here. So core QXY is equal to the volume of the core. I'll just say volume VC for core of, what am I doing? Volume renormalized of the hyperbolic manifold is the volume of the convex core plus O of 1. Okay?
So, Jeff, can you say again what you mean by the hyperbolic metric maximizes the renormalized volume?
So if you take, the hyperbolic metric case of I star. Okay, so if we fix an area for this limiting metric of 2 pi times the Euler characteristic, so for any choice of area, a constant curvature metric maximizes this W volume. Okay, and the hyperbolic metric in particular maximizes it in the case of the Poincare area. So if we take the hyperbolic metric to define the W volume, that gives us this quantity, the renormalized volume.
So this is like the maximum over all sort of things, sort of convex core, not convex cores, but
right. Okay. So there's a missing statement here, which is that if you take different convex surfaces here, this quantity W of n or if you take different convex submanifolds, if you get this particular metric at infinity, then the W volume only depends on that metric. So you can reconstruct the W volume from the metric by constructing a convex submanifold, and one way to do that is to use this notion of the Epstein surface. So there's sort of an envelope of horospheres that defines a convex submanifold, where you sort of estimate the set you look at the set of points where the metric at the boundary is larger than the visual metric, and that determines a horoball. You take the envelope of that family of horoballs, that gives you a convex surface. And then you could start with that as a definition from the metric at infinity and build the W volume from that family once you show that it's invariant under the particular choice of Epstein surface. Okay? So, and the Epstein surface comes from the metric, and then, yeah, they show that it's maximized in the case of the hyperbolic. I mean, it's an easier way to do it to just say, start with a hyperbolic metric, take the Epstein surfaces, define the W volume that way. That's the renormalized volume. I was trying to give a little more history of the ideas. Okay, so again, so you have this relationship to the convex core, but there's also a variational. So if we vary, let's just do it like this, okay? Let's say we vary, because there are various ways to say this, but if we vary one of these surfaces in Teichmuller space, the first order variation, we get a tangent vector, which is a Beltrami differential, okay? And there's also, what they show is that this looks like the integral over S of a certain quadratic differential, which we'll call phi sub x, which is the Schwarzian times the tangent vector. Okay, and this is just the standard product between quadratic differentials and Beltrami differentials. But this particular quadratic differential is the Schwarzian on x. Okay, so sometimes you think of, when you're taking a path, you look at Schwarzians on y instead of Schwarzians on x to get the Beers embedding. But here we're actually taking the Schwarzian of the structure associated to the side that's varying. Okay, and this gives us its variational formula. And why is that good? Well, maybe because I want to get to some other things. The idea is that the Beers embedding is bounded, okay, by Nahari's estimate. So Nahari tells you that phi x absolute value over the Poincare metric is actually bounded by 3/2. Okay? So then you can work explicitly in whichever norm, the Weil-Petersson or Teichmuller. If you take a continuous family starting at y and going to x, a path in Teichmuller space moving at unit speed, and one gets out of this that the renormalized volume, qxy, is bounded by 3/2 times, well, the area times the area, right, times the Weil-Petersson norm of this guy. So that gives you the length of the path from x to y times this explicit constant using Nahari's formula. That's, again, it's sort of the Cauchy-Schwarz inequality. You have, okay, so if we were to really do this explicitly, this looks like phi x dz squared. This is x tilde dz bar dz. Okay, so that's going to look like an area form. So this is phi x x tilde times dz squared, right? Now you divide, so you take rho squared, x dot dz squared. This falls out because of the Nahari bound. This you have to do Cauchy-Schwarz on splitting the rho squared into 2 rows. One of those gives you Weil-Petersson. The other gives you area, but you're taking the square root because it's Cauchy-Schwarz. Okay? Okay. I kind of had a feeling that was longer than I wanted, but in any case, so that's, I mean, it's a beautiful thing though, right? So suddenly you have volume explicitly given here in terms of some integral. So I guess I should mention that as intuition, this variational formula is kind of a continuous version of the Schlafly formula. So, you know, the derivative of the angle is like the derivative of the volume. And here, embedded in the renormalized volume is this notion of mean curvature. And as you're sort of varying the mean curvature, you're varying the volume. So this is some kind of, I guess this is due to Riven and Schlenker in the version that they need here. So there's no use of combinatorics in particular, which I don't know, maybe it's putting us out of work, but it's very pretty. Okay. So I wanted to say a few things about the applications here. So in terms of systols and diameters, Weil-Petersson, I should also mention, let's see, I didn't give appropriate credit, and I of course meant to. So this was shown also independently by Kojima and McShane. And they proved the WP case without the N, but I think they could probably work out the N case. Okay. So in the Weil-Petersson case, I guess you can use the fact that we know the smallest volume closed hyperbolic 3-manifold, or we know what the volume of it is, to show if we take the closed surface so that the 3-manifold that fibers over the circle is closed in particular, and we take the Weeks manifold, which is the 5-2, 5-1 Dane surgery on the Whitehead link, that its volume over 3 times square root of pi times g minus 1, this is just some perturbation of this area square root, is less than or equal to the length of the systole in the Weil-Petersson metric of the moduli space of S. Okay. So I mean, this is just the length of the translation distance for the smallest monodromy. On the Weil-Petersson moduli space. And it's an explicit formula. So likewise, so I guess this is, let's see, and in the punctured case, right, so I wanted to say what the volume is. So the volume here, this Weeks manifold is 0.9427. And this was due to Gabai, Meyerhoff, and Millie. Yes? Is that correct? Yeah, that's what I mean. Okay. Okay, so in the case where the Euler characteristic of S is negative, but it has boundary, well, then we know that the 3-manifold that fibers over the circle with smallest volume is the figure 8 knot complement, which is twice the volume of the regular ideal tetrahedron. So that leads to the formula for thirds V3, where this is the volume of the regular ideal hyperbolic tetrahedron over the area of S is less than or equal to the length of the Weil-Petersson systole of the moduli space. So what?
Where do you get this bound from? How do you know that that's the
Okay, so what we know is that the smallest cusped hyperbolic, the smallest volume cusped hyperbolic 3 manifold has volume of the figure 8 knot complement.
Oh, I see. No matter what the genus was. That's
Right. Yeah. So you could write in the middle here, volume of smallest single cusped hyperbolic 3 manifold. But then you have to put the genus in the denominator, right? So it gets smaller as the genus goes up. But
so that you don't expect it to be sharp to be the
oh,
smallest genus G guy should be bigger than this.
yeah, I don't really expect any of these to be.
But it should be bounded above, right? You can have things that fiber of arbitrarily high genus with uniformly bounded volume.
Right.
Oh, I see. So there actually should be some number of this form.
It should be, you know, there should be some function of G and that goes up, but it does hit a limit. It doesn't like
Mm-hmm.
Right.
Right. That's where veering triangulations come. Okay, so
I mean, for the closed case, John Albert and I have conjectural like
right, yes.
small volume.
Keep meaning to embed that conjecture into this talk, but it's sort of hard to do. So the last thing I want to say in terms of this diameter statement is about the imaginary axis. Well, how would you get the imaginary axis from this? It's not a pseudo-Anosov axis in moduli space, but it actually sort of is. So if you take, it's a limiting. It's one of these sort of billiard paths on moduli space I talked about. So if we take psi n to be 1n, 0, 1, 1, 0, n, 1, what does that do? It's basically you twist n times about alpha, and then you twist minus n times about beta, where you have a longitude meridian pair. So these volumes stay bounded, the volumes of the mapping tori. What does the axis do? Well, if we think about H2 modulo SL2Z in the Weil-Petersson metric, that looks like the modular surface, but with a finite cusp. So the axes, as one twists higher and higher order, well, they wind n times around this way and then back, catch some homotopy, and then wind n times again. Okay, but the cusp is very sharp in the Weil-Petersson metric. So in fact, as n tends to infinity, these axes limit to a path. I'm just going to be bold and suggest that it looks like this. It goes straight out to the cusp and back. So it sort of goes over the imaginary axis to 0, and then back down the imaginary axis to infinity. Well, from 0 to infinity, and then you sort of miss the rest of it because it's getting wound around by this factor. But the limit of the axes, so the limit of the length of Weil-Petersson translation distance of these elements is equal to twice the Weil-Petersson length of the imaginary axis. So you can see this length in terms of the translation distance of this guy. So I just want to conclude with that observation. So in particular, the volume in this case of the mapping torus is 3 times the square root pi over 2 times the Weil-Petersson translation distance, which converges to 3 times the square root of pi over 2. Here we have no area because we're just in the Teichmuller space of the punctured torus, so it's just pi, 2 pi. So that's the length of the Weil-Petersson in the Weil-Petersson metric of the imaginary axis. So in particular, you have a sort of Weil-Petersson in radius to Teichmuller space of bounded below by 1/3 2 pi times the volume of the ideal octahedron. Because this manifold in the limit is just the complement of the Borromean rings. Okay. So that gives estimates on the Weil-Petersson diameters as follows, and then I'll stop. So for the once-punctured torus, the Weil-Petersson diameter of the moduli space is bounded by 2 pi times this volume of the octahedron for M04. It's twice that. Okay, and in general, for Gn, the diameter is bounded below by 1/3 root pi times this V8 times the square root of 2g plus n minus 4. Now, I'll just mention that there was a discussion in Cavendish-Parler's paper that they would hope that this is not optimal in terms of the genus growth as a lower bound, but just in terms of the asymptotics. But at least they get that much. So, and this just has to do with the fact that you can always find some product of these bits of this Weil-Petersson imaginary axis embedded in some boundary stratum of the Weil-Petersson moduli space. So that gives you some lower bound to the diameter. Okay, I've been through these constants multiple times. I don't think I'm going to try to attempt to do that right here. But yeah, so right, it should be twice V8. So maybe I'm off by a factor. It could be. All right, so I will review that. I hope it's right, but maybe it's wrong.
Yeah, I think it's a factor 2.
Which factor here?
Yeah. Yes.
Okay.
That should be brought down.
4. Well, this is just the okay. That's immaterial. So let's see.
You didn't bring it down to here. To the next line. Yeah. No, over to the right.
Okay, so. Or then okay, I'll check it. I'm not going to make any claims that will go on a videotape distributed to the universe. Okay. All right, thanks very much. Sorry.